All right, I think we're good to go.
Okay, should I begin? Okay. So, so before I begin talking about the protocol, I want to first recall what the standard prepare and measure scenario is. Okay. So prepare and measure scenario. So Alice and Bob are species separated. Alice prepares an arbitrary quantum state at her end. So the quantum state rho is of dimension dq. And it is a semi-definite positive matrix. And the trace of the state is equal to 1. Right? So it is dq by dq matrix, right? Then once she has prepared her quantum state, she sends it to Bob. And what Bob does is after Bob receives the states, he performs some POVM measurement, right? And the notation that we are using over here is being subscript P, such that we have these operators are also semi-definite positive matrices, and the summation over all the possible outcomes. So here the small letter b represent the possible outcomes. So if we take the summation over all possible outcomes, it would be equal to identity. Right? And then the probability of outcome B is represented by the probability distribution over here. Which is just trace of the state rho and the operator that Bob has chosen, right? So this is the standard prepare and measure scenario where the communication from Alice to Bob is actually a quantum state, right? And the standard classical simulation model so Alice and Bob share some random variable, lambda, right? With probability distribution pi of lambda. So it is essential to remember that. Then Alice uses lambda, right? And so in a classical simulation model, the idea is that Alice and Bob are species separated. Alice uses the quantum state at her end, and then she uses the random variable lambda, the resource that both Alice and Bob share. She uses that, and she chooses a classical message, right? So she chooses a classical message to send to Bob. And this classical message belongs to this set where the highest number is DQ. Recall that in the prepare And major scenario, DQ was the dimension of the state row. And again, with distribution, P of A. So this is a distribution over Alice's message. And now once she has sent her classical message, Bob receives it. See, and then uses lambda and B. This is the POVM, right? To output B. Okay, with distribution. P. So now Bob classical message, right? And the entire protocol is presented by this. Um, D of lambda, then P of A, where P of A, P of B, and this lambda right, right? Where this P of A is the probability distribution with which Alice chose her classical message. P of B is the distribution over which Bob produced his output B while choosing the POVM, while performing POVM, right? So, and the claim is that these two these two probabilities are equal. Right? So, um, the minimum number of bits they consider uh, they Alice 2 bits of communication, classical communication actually
Ramla, voice
simulate
is breaking up a bit.
So any
Maybe
questions
just
so far?
pause. So the last few sentences, I think, could be repeated. Ramla, could you just repeat the last couple of sentences?
Idea is that
Hi, Ramla, can you hear me?
so I'm back. Could you make me co-host so I could share. Yeah. Okay. So prepare, and this is a standard prepare and measure scenario where we are simulating the correlation by using the classical simulation model, which I have described over here. And the result is that for a single qubit case, the minimum number of the necessary and sufficient number of classical message that Alice needs to send to Bob, excuse me, is 2, right? And for that, they provide this optimal protocol. And before I actually start talking about the protocol, few things I like to mention that in this, Alice and Bob share 2 vectors. Lambda 1 and lambda 2. So, am I audible?
Yes.
Yeah. Okay. Good. Okay. So, Alice and Bob share 2 vectors, lambda 1 and lambda 2, such that they are independent. Uniformly distributed over the space. And they are unit vectors. So they actually exist in a unit radius sphere in R3. Okay. So some of the relabeling that has been used is this the quantum state that Alice prepares can now be rewritten like this. Right. And over here, so the idea over here is that any mixed state can be represented as a context combination of pure states, right? So without without any loss of generality, what they're doing is we are considering the rho to be a pure state, right? And so over here, this one is the identity matrix, where else this sigma is the matrix where the entries are y. So where these sigma x, sigma y, and sigma z are the poly matrices. So these 3 vectors are actually these are 3 poly matrices are the basis of polygroup, right? And along with identity. So should I actually write down the matrix form of these matrices as well?
No, that's fine.
Oh, that's fine. Okay. So okay. Secondly, another result that you use that every POVM can be is actually can be presented as a rank 1 projector, right? So they consider only rank 1 projectors, which is this is a matrix multiplication of a column vector with this row vector, and which can be further simplified like this. So these two these 2 vectors x and y, they are they are unit vectors, and they also belong to in the space R3, such that so it is interesting to note that once Alice prepares her quantum state, she only needs the information of this vector x to actually access this quantum state, right? So the entire information about this quantum state is actually stored in this vector x, And similarly for the POBM, YB is the vector that actually telling us about the measurement operator. And also this probability P of B is the distribution over the outcomes, possible outcomes. Distribution over possible outcomes. Right. And one other thing that I would like to discuss over here before actually talking about the protocol is this Heaviside function. Setting up the class message. Right. So this is very useful. And one other thing I would like to mention is this the inner product of the vectors, right? So in the inner product of any two vectors u and v is represented as cos of theta, right? Where theta is the angle between the two vectors u and v. And if these two vectors are actually unit vectors, if u and v are unit vectors, then the inner product is just cos of theta, where theta is the angle between u and v, two vectors. And once we compute, so if we compute the Heaviside function h of uv, and it tells us otherwise. So what does it tell us? It tells us that the output of the function would be equal to 1 if the theta lies between pi by 2 to minus pi by 2. Right? Because over here now cos theta is actually lying between over here the cos theta is actually lying between 0 and 1. Right? Is that clear?
Any question from anyone so far?
This is actually important because I'm going to build up the intuition of the protocol based on this observation. Okay. You can just stop me anywhere if you have any question, and you can ask a question. Okay? What is protocol? Okay. In the classical simulation model, right? So we proved the authors proved that Alice only needs 2 bits of classical communication to actually successfully simulate the quantum correlation in the standard PM prepare and measure scenario, right? And for that, the protocol says, so the first step is that Alice prepares her quantum state, right? And recall that we have now rewritten the quantum state rho in terms of this vector x over here, right? So one way to go about it would be this, that Alice just sends her entire coordinates of her, state of her vector, X to Bob, but that would actually take infinite amount of communication. So what she does is, once she has prepared her quantum state, now she selects her 2 bits. She chooses her 2 bits. Let's see. Okay. So she sets up she takes the inner product of her vector X with lambda 1 and lambda 2. And recall that lambda 1 and lambda 2 are the 2 vectors that Alice and Bob both share. So Alice and Bob both have the information about lambda 1 and lambda 2, right? Now, what happens? Why is she using this, this function to compute her 2 bits? So it is equals to 1 if the inner product is greater than or equal to 0, and it is equal to 0 if the inner product is less than 0. So again, the just like I previously mentioned over here, so if the inner product is greater than or equal to 0, that would mean that let's call this theta1 is angle between x and lambda 1. Okay, so if this is greater than or equal to 0, then that would mean that theta1 actually lies somewhere between pi by 2 and minus pi by 2. And if it is negative, then that would mean it lies somewhere else, right? And that would be, the bit would be equal to 0. And similarly, the same argument holds over here. And we will see in the next few steps why this is, why they are setting up these classical bits like this. Okay. So in the next step, what Alice does is Alice sends these 2 bits to Bob. Right? And after receiving these 2 bits, what Bob does is Bob sets 2 vectors lambda 1 prime and lambda 2 prime such that right. So Bob sets 2 vectors, define 2 vectors, lambda 1 prime and lambda 2 prime with the help of this formula. What does this formula tell us? So it tells us, okay, you know what? If the qubit, if the classical message C1 is going to be 0, so what Bob is going to flip his vector lambda 1. So let's try to see this thing. What does that mean? So this is X, lambda 1 and lambda 2. So Alice has access to X now, and she has access to lambda 1. And Bob and Alice both have access to lambda 1 and lambda 2. So once what she's going to do, she's going to take, she's going to compute C1 and C2, right? And you can see that okay, so the angle between lambda 1 and X is less than pi by 2, right? So this is going to be equal to 1. Whereas C2, the angle between Alice's vector X and lambda 2 is actually greater than pi by 2, right? So this is going to be 0. You can actually compute it by the help of this formula, right? And so what happens when Bob receives C1 is equal to 1 and C2 is equal to 0? So Bob is going to set up lambda 1 prime to be equal to lambda 1. But in the case of C2, lambda 2 prime is going to be minus lambda 2 prime. So he's going to flip it. Right? Why is he doing this? What is the main reason? What is the goal? So the idea is actually behind flipping these vectors is this, that Bob wants both of these vectors, lambda 1 and lambda 2, in the positive hemisphere of the vector X, right? So as you can see, so, okay, hopefully this works, actually. Right? So in this is the vector X, right? So you take pi by 2 on each side of this vector X, and you define this positive hemisphere, right? And so the goal, so up till now, what Bob has been trying to do is Bob has been trying to define these two vectors such that these two vectors are actually lying in this positive hemisphere of X. And one thing I would like to mention this drawing is actually 2-dimension, right? But this is like a projection of unit radius sphere into 2-dimension, right? Just to make things clear, the intuition behind it. Any questions so far?
Can you explain again how did you compute C1 and C2?
So C1 and C2 are being computed with the help of this Heaviside function. And I define the Heaviside function over here. So for given any number, Z, the output of this function is equal to 1 if this number Z is actually or equal to 0. And the output would be equal to 0 otherwise, right? And so when we consider any two unit vectors, U and V, and we take their inner product of U and V, and that is equals to cos theta. This is the definition of standard definition of the inner product, right?
Yes.
And we impose another condition on it. These two vectors are actually unit vectors, so the length of these two vectors would be equal to 1. So this denominator would be equal to 1, and then we have the inner product is equal to cos theta, where theta is the angle between these two vectors, U and V, right? And so the input of this function would be the inner product of these two vectors, unit vectors, right? So this is the definition of the function. Now, we know that cos theta actually lies between -1 and 1. So when we set this cutting off point over here 0, what we mean that now this cos theta actually lies between 0 to 1. And you can easily verify that in 0 to 1, the angle actually theta actually lies between minus pi by 2 to pi by 2.
Yes.
Right? So okay. So in the protocol, when Alice is preparing her 2 bits, C1 and C2, she's using this Heaviside function, and she's using the inner product of her vector x with this shared 2 vectors, lambda 1 and lambda 2. Remember that the resource shared between Alice and Bob is actually lambda 1 and lambda 2, 2 unit vectors. So both of them have access to lambda 1 and lambda 2, but now she has x, and she compute this Heaviside function, where the input of this function is actually the inner product of x and lambda 1, and then again x and lambda 2. Okay, so whenever the angle between x and lambda is lambda I, it could be lambda 1, lambda 2, is going to be between minus pi by 2 and pi by 2. What does that mean? That means it is defining a positive hemisphere that of x, right? So this is the vector x, and you take 90 degrees over on each side, and then you have this positive hemisphere. So these bits C1 and C2 are going to be equal to 1 if the vector lambda 1 or lambda 2 actually lie between inside this hemisphere, and it is these bits are going to be 0 if they lie outside of this hemisphere. That's the first step. Yeah, go on.
I just had one doubt that when we initially took lambda 1 and lambda 2, we said that they are unit vectors which are uniformly distributed.
Yes,
So,
yes.
So because of that uniform distribution, will it always be true that at least one of C1 and C2 will be equal to 1 and the other one will be equal to 0? Or they can
No,
be
not necessarily. They are independent as well. See? So so lambda 1 and lambda 2 are independent. They are not correlated in any way, right? And they are uniformly distributed. What does it mean? On a unit sphere, so the probability of any vector being selected is actually going to be 1 upon 2 pi. Right?
Yeah.
So any vector on the unit sphere that can be, what is the probability that you choose any vector on this unit sphere, and you say, okay, what is the corresponding probability? So that is going to be 1 upon 2 pi. Does that make sense?
This case that you discussed where C1 is equal to 1 and C2 equals 0, this is one of the 4 cases. I mean, we are discussing a particular case here.
We are discussing the protocol. This is how they are defining the protocol.
Okay.
So this is the method that they are using with which Alice is preparing her 2 bits.
Oh, okay.
Right? And the whole thing is once Bob receives these 2 bits, C1 and C2, he immediately gets to know about it. If the bit is 0, then he would know, for example, if C1 is equal to 0, then he would know immediately that, you know what, C1 does not lie within the hemisphere of the vector x. Bob has no knowledge of vector x. Only Alice has the vector x, right? But Alice is telling something about it to Bob by sending C1. If Alice sends C1, Bob immediately C1 is equal to 0, then Bob immediately gets to know, okay, you know what? This vector lambda1 does not lie within if C1 is equal to 0. Okay, so it does not lie within the hemisphere of positive hemisphere. And then if the C1, the bit is equal to 1, then Bob immediately gets to know, okay, you know what? This vector lambda1 is actually lying within the positive hemisphere of the vector x. So what
Okay.
happens? So if Bob gets to know, okay, you know what? The vector is actually lying within the hemisphere, then he doesn't do anything to it. He define the new vector as it is. Just in this case, over here, he says lambda1 prime is actually equal to lambda1. But if the bit is equal to 0, then he needs to do something about it because he wants his both of these vectors in the positive hemisphere of x. So what he does, so what he's supposed to do, he's supposed to flip the entire vector. Could you actually excuse me just one moment? Okay, so I'm back. So any questions so far?
In particular, in
Am
terms
I
of the
audible?
implementation task, in terms of the implementation task that you have, any questions regarding how to proceed with the implementation, everyone? I know, Jose, you had questions about Lambda. Hopefully it's a bit clearer.
Yeah, the use of Lambda is clear now. That I understand now that it's something that they know before starting the protocol.
Okay. So shall I continue? Next steps. Okay, you can just ask me any question if you have. Meanwhile, right? So so remember that we have set up this equality. Okay. So now what happens? So Alice has this set of POVMs, right? Or you can, I shouldn't say set of POVMs, just POVMs. It's a set of operators. So where we have defined this operator by these with the help of this particular vector y of p, right? And so recall that p of b is actually the distribution over all possible outcomes b. Now so Bob picks some vector y of b according to the distribution p of b, right? So this is the vector actually So this is a vector of y of b that Alice has picked with some distribution p of b. Okay? And now Bob sets, not Alice actually, Bob. So now okay. So now Bob picks a vector lambda. Now he's going to set it to be equal to lambda 1 prime or lambda 2 prime on some criteria. What is the criteria? If the inner product of lambda 1 prime with this vector y of b is greater than the norm of this inner product is actually greater than the norm of the inner product with lambda 2 prime, then he's going to select lambda 1 prime. So what is the intuition behind it? What is he trying to do? And why is he trying to do this? So remember that now when we say that, so these are two vectors. So these are two vectors, right? And we say we are taking the norm of the inner product. So we are saying that we are taking, this is equal to cos of theta, where theta is the inner product, is the angle between u and b, and we're taking the norm of this inner product, right? So the value, now the values actually lie between 0 and 1, right? And when we say that, so let me rewrite this as cos of theta 1, cos of theta 2. And if this holds, that means theta 1 is actually less than theta 2. Right? Is that clear? So Bob picks a vector y of b, right, according to some distribution p of b. And then what he does is he takes the inner product of that vector y of b with this lambda 1 prime and then this lambda 2 prime. And he takes the norm of those inner products. And if the value with lambda 1 prime is actually greater than the value with of the inner product with lambda 2 prime, then he's going to select lambda 1 prime. What does it say? It means I just replace this inner product with cos theta, where theta 1 is the angle between lambda 1 prime and y of p, and theta 2 is actually the angle between lambda 2 prime and y of p, right? And if this inequality holds, that actually means that the angle between lambda 1 prime and y of b is smaller, or you can say it's less than or equal to the angle between lambda 2 prime and y of b. So he is choosing the closest vector. He's choosing the vectors lambda 1 prime or lambda 2 prime, depending which one is closest to y of b. Does that make sense? Is that clear?
Wouldn't a counterexample of that would be that if one of the angles is p halves, then the cosine of that angle is 0. But if one of them is, for example, pi, then the cosine would be -1. If we take the absolute value, that's 1. So that cosine is bigger, but the angle is also bigger. So that intuition
but
of
there exists this symmetry, right? There exists this symmetry because do you remember the wave function? So okay. Yes. It is pi by 2 minus pi by 2. Look like this, right? Okay. Right? So the wave function would be something of this sort. So, form. And so what you were saying is that it would be somewhere here. The one. Can you repeat your question?
that if, for example, theta 1 is it's pi and theta 2 is pi halves, we see that that theta 1 is actually bigger than theta 2, and the absolute value
So,
of the cosine of theta 1 is also bigger than the absolute value of the cosine of of theta 2.
so you're saying theta 1 is pi and theta 2 is actually pi by 2,
Yes.
right? So then the cos of theta 1 would be actually greater than no, it wouldn't be, right? Because this is greater than 0 and this is just 0. So one of the angle between theta this is going to be pi and this is going to be pi by 2, something of this form. Yeah, yeah, okay. So you're saying theta 1 is just equals to pi, and then this is equals to theta 2 is equal to pi by 2. I'm lost somewhere in between all these stuff.
I think we can review the details later. One thing to verify would actually just be by testing this in the implementation itself as well. So any concerns we have about the validity of the protocol can also be tested by just testing the actual implementation.
Yeah, the
So,
thing that's bugging me is the absolute value, because if we get rid of the absolute value, then yeah, it's true that the the
But
larger the
we
cosine of the angle
Mhm.
is, the further apart
Mhm.
the vectors are. It's the absolute value, the one thing that's not making it work for me.
So actually, if you just look at this drawing over here, you can see that this lambda 1 prime and lambda 2 prime are actually existing in the positive hemisphere of X, right? And I purposefully I chose this vector to be y of b, which is outside that positive hemisphere, because if it is inside that positive hemisphere, things are much more easier, right? And the angles would be somewhere between pi and 0. But I'm okay. So it is outside the positive hemisphere, and now what we want to see is that when we compute the angles between this vector y of b and lambda 1 and lambda 2 primes, they are definitely going to be greater than there exists this at least possibility that these vectors are going to be um you know other would lie the angle between these vectors would lie somewhere outside this just minus pi to pi, right? So these vectors are actually lying the outside the positive hemisphere of the vector y of b itself. And that is also one of the crucial steps in the proof of the protocol, where they were just computing the probability distribution in Appendix A of the paper, where they were saying, right, so it is interesting to note that the positive hemisphere of this y is actually this you know this half circle, and lambda 1 prime and lambda 2 prime, both of them are actually lying outside these vectors. So hence we have this norm on the cos theta, right? And you can actually verify this. We can actually verify this this implication over here, where if cos theta or norm of the cos theta 1 is actually greater than cos theta 2, and then the angles have this inequality where theta 1 is actually less than theta 2. And so the interesting thing to notice is this, we have this symmetry over here because of these norms, right? And because of these norms, we can only consider these angles between 0 and pi by 2, and you can actually verify that and work out the details, right? We can discuss it later on as well. I hope that actually provides some useful insights behind setting this lambda. So far. Okay. Then after setting this lambda, Bob outputs P. P with probability. Okay, so remember that this function over here is defined like this, where if the input is greater than or equal to 0, the output would be the input is itself, and the output would be equal to 0 if the input is less than 0, yeah. And this P of B is again the probability distribution over all possible outcomes. Okay. And then we have the summation over there, which is not just a normalization vector. So this sums up the protocol itself. So in the paper, they have actually used a modified version of this protocol where there is this two-way communication between Alice and Bob. Alice sends one bit of so Bob sends one bit to Alice, and then Alice sends one bit back to Bob. And this, which is a modified version of this protocol. Should I continue with this? Because the actual proof in appendix is actually for the modified version. And it is interesting to note that even though the communication between Alice and Bob is slightly modified, the statistics produced by both of these protocols are exactly the same.
I would say let's take a pause here and see if how do the first few attempts to implement the protocol go?
Okay.
Does that sound okay?
Sure. Yeah, sure.
So would this be enough for everyone to kind of get started just implementing this protocol itself?
For me, yeah, I think this is enough to start trying to implement this protocol. Now, with the modified version that only uses one bit of information, I'm kind of confused because the paper only mentions that it's one bit that Alice sends to Bob, and Romla just said that it's a two-way communication, so I'm confused there.
No. So this is the protocol. This is the protocol that they have defined and then modified this protocol and define another one, which I haven't discussed it really. So let's just consider this protocol where Alice sends two bits of two classical bits to Bob, and then Bob chooses his measurements and produces outputs B, right? So let's not talk about the two-way communication protocol that come later on.
Okay.
Okay. So are there any queries related to this? Is it? Right.
When we talk about the probability distribution of Y sub B, which is the measurement that Bob chooses, the only condition that this probability distribution needs to have is that no Y sub B has more probability than the others, for example.
Sorry?
Like
what is the condition?
all Y sub B's that Bob can choose all have the same probability. There's no one that has a bigger probability than the rest, for example.
So are you talking about this probability distribution over here?
Yes.
So this probability distribution, if you think about the prepare and measure scenario, where the correlations were quantum, if you think of it this way, then this probability distribution was defined on the POBM measurements. So this is actually, it is a set of all possible outcomes, and then there's there's this distribution, probability distribution defined on this set of possible outcomes. And when we say Bob picks up this vector according to the probability distribution, so let's say B belongs to some set of possible outcomes, right? So when Bob picks YB of 1, so what is the probability with which Bob is going to pick this. It's going to pick this vector that corresponds to B1. Is that clear?
Yeah, yeah.
So would 1 week be a good time then to kind of meet after with maybe an initial implementation?
I just had a query that I mean, I don't have much background in simulation and all. So can you just provide a brief outline of what exactly I need to do in the implementation part?
So the other thing is, since there are three of you, it doesn't necessarily need to be where everyone is working on their own independent iteration of the implementation. It seems like, Jose, you have a general idea of the entire protocol. So maybe you identify the structure of the implementation and then just provide the other members brief descriptions of the functions that they need to implement that you can then combine together for the entire protocol itself.
Yeah, I can try to give an overview of the steps of the protocol.
And also in terms of the kind of taking those steps and then thinking about them as individual modules or functions that need to be implemented in the code. And so each member has some particular functions to implement them. So then it's still a group kind of contribution. Does that work for everyone?
Yes, sir.
Yes.
Okay. So maybe just share something on GitHub or GitLab repository, and then just share the link on Discord whenever there's something to review. I sense that's not okay. Or are there still concerns or queries?
I can try to make a GitHub repository on my profile and share it on Discord, so we can work on the project there. It would just be probably a Python file that can be downloaded and modified in our individual computers, and then just upload the modifications to the repository. So I can do that, make a repository and share it on the Discord.
Yeah, I think that sounds reasonable. It's just that I guess within that file it should be clear, and I guess Jose, that task might be yours then in terms of which functions would be implemented by which members.
Excuse me?
So within the code file, I guess you might have to take the lead in terms of identifying which part of the code gets implemented by which group member, or whoever kind of seems more interested in implementing a particular part of the function.
I guess we can discuss first in the Discord who's going to take each function once the overall structure of the protocol is defined, and then when updating the main file, which contains the whole protocol, whoever made a function can maybe leave a comment saying name and the name of whoever made the function, so we all know who made stuff. Also, the username appears when a pull
Right.
request is made, so I can also use that to review who sends what.
Right. Does that work for everyone?
Yes, sir.
Yes.
So I think the first task would be for the three of you to meet up to make sure you understand the code structure that you'll have for the implementation, and then distribute the task among yourselves. All right. Any other questions before we break up for today? Does that seem a reasonable step forward?
Personally, I'm a bit worried about the implementation part, and although what you say gives some, I mean, I'm just a bit worried about what we are going to do, because I haven't done any of it before. So
So you're
I
right.
can't.
I'm assuming that, so you have some programming background, right? So we are not necessarily asking you to structure the entire simulation yourself, but if you were given the task of implementing some particular functions with clearly identified behavior, would you be okay with that?
Yes, sir. Yes.
So I guess that's what I'm hoping, that within kind of maybe your next couple of conversations, you agree upon the structure led by Jose about what the structure of the overall implementation would be. That's what Jose mentioned as well, that there can be a discussion on Discord about how to decompose this protocol into individual kind of functions. And then if you understand a particular function well enough, you can take the lead on implementing that. So don't necessarily think about the entire simulation, but just particular functions that need to be implemented that carry out a task. So you really kind of think of the protocol itself as having something that you give it as input. The protocol gives you something as output. You really essentially want to simulate that behavior. It's not really a physics simulation per se, right? It's more of a, just say, I want to just do the calculations of this protocol in code. So it should be relatively straightforward.
Okay, so I'll try with the group once, and I'll get back to you, sir.
Yasmin, any questions?
No, thank you.
All right. I guess we'll call it a meeting and then continue the conversation on Discord. Please feel free to post your questions there. Thank you, Ramla. And if there's progress on the implementation, then we can continue the conversation with Ramla as well in our next meeting.
Sure.
All right.
Thank you.
Thank you, everyone.
Thank you.
And Yasmin, could you please just share the link to the recording on Discord?
Yes,
And
yes, sure.
Ramla, if you can just share a PDF of the lecture
Sure.
notes. All right. Yeah. Thank you.